Welcome to this session on semiconductor devices. The devices that we'll be seeing are varactor diode, UJT, and Schottky. And for each of these, we'll be looking at the principle, the characteristics, and its application. So first, let us look at the varactor diode. Varactor diodes are the ones whose internal capacitance they vary with the variation of the reverse voltage. The capacitance can just be changed by changing the voltage across its terminals. It is actually used for storing of the charge. These diodes they generally generate less noise compared to other diodes, and they are also very small and lightweight. In these diodes, the concentration of impurities varies such that they are lesser near the PN junction, and they gradually increase as we move towards the layer's outer surface. Because of the difference in the way the impurities are added to the P and N type layers, the capacitance of a varactor diode is always higher than that of a conventional diode. These varactor diodes are also known as varicap, tuning, or voltage variable capacitor diode. So here, when how the principle works is, it is very similar to that of a variable capacitor. So in the variable capacitance also, what we saw that the capacitance is proportional to the area, but it is inversely proportional to the width. So this same principle is what is happening over here, because we said that the depletion layer is almost similar to that of the capacitor's dielectric medium. Okay, so here also the junction capacitance that is formed is inversely proportional to the depletion layer. As the reverse bias voltage is increased, what happens is the depletion region width will increase. When the width increases, then it results in a lesser capacitance. The capacitance will decrease. Or with a reduced reverse bias voltage, the width reduces, which results in an increase of the capacitance. Okay, this is about the working of the uh, Barrett diode. So if you look at the characteristics, it's the same. Okay, for a lower reverse bias voltage, you find that the capacitance is more. See, it's almost 100 picofarads, whereas as the reverse bias voltage keeps on increasing, you find that the capacitance reduces. You see, it's almost 15 or 10. Okay, so they are inversely proportional. So the value of the reverse bias voltage, it should be below the breakdown voltage. Okay, because above this, the value of the capacitance equals 0 because of the breakdown of the depletion region and the free flow of holes and the electrons. The applications of the varactor diode can use it in RF filters, can use it in voltage control oscillators, high frequency radios, band pass filters. See, where all you are supposed to make it to act as a capacitance, as a variable capacitor. Okay, so there all you will be able to find the applications of the varactor diode. Next, let's look at the Schottky diode. Schottky diode. So before looking at the Schottky diode, let's look at one concept. You will be able to connect a PN diode in a forward bias as well as in a reverse bias. When you connect it in both the cases, we will have the depletion region that is being formed. When you connect it in a forward bias, the capacitance that is formed is called as the diffusion capacitance. When you connect it in the reverse bias, the capacitance that is formed, you call it as the transition capacitance. The diffusion capacitance usually restricts the switching speed, and the transition capacitance will decide the frequency of the reverse switching operation of the diode. So a smaller value of these capacitance are required for higher frequency of operation of the diodes. Schottky diode usually has almost zero diffusion capacitance and a smaller value of transition capacitance. So these Schottky diodes, you also call them as the barrier diode, a low voltage diode, or a Schottky diode. So here, instead of piece-type semiconductor, usually you fill it up with a metal. The metals will be mostly aluminum or platinum, and it does not have the capacity to store the charge at the junction, because you don't have a N and a P together. It is not able to store the charges. So because of the absence of this depletion layer, results in this condition. And this also acts as a unipolar device, and they have a unipolar devices because You see there's only one type of semiconductor, which means there's only free flow of one charge carrier. So because of this you call it as a unipolar device, and they have a low barrier potential compared to a PN diode. So let's look at how you can make the let's look at the working of the Schottky diode. Okay, before looking at the working, this is the symbol of the Schottky diode. It's almost similar to a zener, except that you have a S towards the cathode end. So looking at the working of the Schottky diode, uh, under an unbiased condition in a normal mode, as soon as you fuse the metal and the N layer, you have a smaller amount of depletion layer. It won't be a bigger one as you usually get in a PN diode, but you will still have a reasonable amount of depletion layer. Once you connect it in a forward bias, this depletion region also starts thinning and disappearing. So you look at the width of the depletion layer in the unbiased condition and compare it with that of the forward bias depletion region, you can find that this depletion width is reducing. When you connect it in a reverse bias, the width will start increasing. Okay, as the reverse bias keeps on increasing, the width increases when at a particular point the current flow stops. An abnormal increase in a bias voltage, this depletion region will break down and the device will be damaged. So this is how a Schottky diode works. So this working is almost similar to that of a PN diode only. So characteristics will also be similar, but only thing, because because of the amount of charge carriers that is going to be less, you will have a steeper characteristics of a Schottky diode. The forward voltage drop is less compared to that of a PN diode. It increases by increasing the doping concentration of the N-type semiconductor. The VI characteristics, the why you say this is steeper is because of higher concentration of the charge carriers. Okay, so this is about the working of the uh, varactor diode. So if you look at the characteristics, it's the same. Okay, for a lower reverse bias voltage, you find that the capacitance is more. See, it's almost 100 picofarads, whereas as the reverse bias voltage keeps junction capacitance. So because of the switching speed, you find its applications in TTL diodes, and also they are used in voltage clamping applications. So this is about the Schottky diode. Next, let's look at the Schottky diode. Schottky diode. So before looking at the Schottky diode, let's look at one concept. You will be able to connect a PN diode in a forward bias as well as in a reverse bias. When you connect it, in both the cases, we will have the depletion region that is being formed. When you connect it in a forward bias, the capacitance that is formed is called as the diffusion capacitance. When you connect it in the reverse bias, the capacitance that is formed, you call it as the transition capacitance. The diffusion capacitance usually restricts the switching speed, and the transition capacitance will decide the frequency of the reverse switching operation of the diode. So a smaller value of these capacitance are required for higher frequency of operation of the diodes. Schottky diode usually has almost zero diffusion capacitance and a smaller value of transition capacitance. So these Schottky diodes, you also call them as the barrier diode, a low voltage diode, or a Schottky diode. So here, instead of piece-type semiconductor, usually you fill it up with a metal. The metals will be mostly aluminum or platinum, and it does not have the capacity to store the charge at the junction, because you don't have a N and a P together. It is not able to store the charges. So because of the absence of this depletion layer, results in this condition. And this also acts as a reverse bias. Until this voltage exceeds this, you will say that this particular diode is reverse biased, and IE will be 0. Okay, so as you keep increasing the voltage, there will be a point where it's called as the peak point voltage, VP. A point of conduction starts. This is when your diode will become forward biased. So when VE becomes equal to VP, the UJT is said to be fired or triggered or turned on. So what happens is, the holes that are from the P type they will be injected into the base region, which will be swept by the electric field towards the base terminal B1. The excess poles implies your resistance RB1 is reduced. So when RB1 resistance becomes reduced, what will happen? It will reduce VRB1. A smaller VRB1 implies a stronger forward bias across the diode. So what will happen? More holes are now injected. So VRB1 is further reduced. Okay. So you find that IE keeps on increasing as VE reduces. So this produces a negative resistance region. So the UJT switches from its off position to on. So this is the region where your UJT is set to be turned on. Okay. So if you look at the characteristics, you can split the characteristics as three regions: the cutoff region, the negative resistance region, and your saturation region. So the cutoff region is where your voltage is lesser than Vp. So here your UJT is set to be in the off position. In the negative resistance region, the VE will be reduced from Vp to the valley point, and here your current will be increased. Current increases while at the same time your RB1 decreases, and this is when your UJT is triggered or fired. And this saturation region is beyond your valley point, where you say that your device is turned on, and you see that VE is almost constant, whereas it's your IE that keeps on increasing. So this is your characteristics of the UJT. And applications, you can use it as a triggering circuit. You can use it in sawtooth generators, oscillators. You can have it in timing circuits. That is all. Thank you.